Alright, so in this video I'm going to be answering some questions and going through some work solutions for the work, energy and power assessment. And so there are going to be 3 different videos for the 3 different questions. So on the first video, these are the questions that I'm going to be answering. I'm not going to be scrolling back up to the top, so you might want to rewind and see what questions I'm answering as I go through. But let's get straight onto it. So we've got a car of mass 850. It's going at constant speed but gaining a vertical height of 60 meters in 20 seconds. So the average power is about 25 kilowatts. Alright, let's get cracking. So let's identify some key information. So we've got mass of 850 kilograms. We've got a change in height of 60 meters. And we've got a time of 20 seconds. So we're going to be dealing with a change in gravitational potential energy. And we calculate that by the mass times by gravity, which at M2 is 9.8, and we're going to times that by 60 to turn that into an energy, and we end up with 499,800. And then to convert convert energy into power, we need to divide it by time, which would give us the average power. And so if we put those numbers in, so we got your 499,800, and it was done over a time of 20 seconds, which is going to give you 24990 watts, which is approximately 25 kilowatts. So we've shown what it was looking for in the question. Okay, so let's crack on. So part 2 wants you to, it says that if we've got a power of exactly 25 kilowatts and there's a constant resistance of 800 newtons, calculate the maximum possible steady speed. Okay, so let's think about some equations we're going to apply. So we're going to be using our power equation. And what we can do is rearrange that to make V the subject. That doesn't look like an F, but it was meant to be an F. And if we take this value of 25, turn it into watts from kilowatts, so convert that out, divide by 800, and you end up with a speed of 31.25 meters per second. So let's move on to part 3. So find the driving force and the acceleration of the car when its speed is 10 meters per second. So let's get some space. Okay, so first off, we can find the driving force at that given speed. So we're going to be using this equation in a slightly different form to last time. We've still got the same power, so we're still going to have 25 times 10 to the 3. We're going at 10 meters per second, so that's going to be this force here. So we've got 2.5 times 10 to the 3 newtons. So now what we want to do is we're going to apply Newton's second law. So whenever you're applying it, it's a really good idea to say it. Like just occasionally some of the exam board decides to reward you for saying what you're doing, and it's just good practice anyway. So we know that the driving force minus the resistive force would be MA. So that means we've got driving force minus resistive force, and that's going to be equal to mass times acceleration. And we put all those numbers in, and we end up with A equals 2 meters per second squared. We end up with a nice number, which is always a nice clue we've done it right. So if we move on to part 4, when travelling on a horizontal section of road, the car goes from 15 meters per second to 20 meters per second in 6.90 seconds with the same power and resistance as before. So what we want to do is find out how far it travels during that section using our work and energy principles. Okay, so let's break this up into the different types of energy change. We're on horizontal, so we don't have to worry about GPE, but we do have to worry about kinetic energy change, and we do have to worry about the work done. So, for change in kinetic energy, it's going to be using your kinetic energy equation. And then substitute those numbers in, and we end up with 74375 joules. That's the change in kinetic energy. So your work done by the engine, or sorry, the work done to change the kinetic energy is going to be the power of the car times the time over which it occurs. But we're going to need to subtract from that the work done against resistance, because that energy cannot be transferred into kinetic energy, so essentially it's like a loss. And so that's going to be the power times the time, which is this one here, and we know that the resistive force is 800. And now we have two equations we can solve for x. So let's tidy up this one first. Okay, and then what we have, we're going to apply the principle of conservation of mechanical energy. So the work done is going to be the change in the kinetic energy, because we're not changing any GP here. And so by doing that, we know that 74375, which was the change in kinetic energy, is equal to the work done. And when we solve that, we can find out that x is 123 meters, and we round that to 3 significant figures. Okay, so that's part 4. So part 5 says when the car is travelling at 20 meters per second up a constant slope, inclined at arc sine 0.05 to the horizontal, the driving force is suddenly removed. The resistance remains 800. What is the speed of the car a further 105 meters up the slope? Okay, so let's make some space. Woo. So let's do a sketch first of all. It's always a very good plan. So we've got this sort of situation here. We've got this angle here, and we know that from the question that this is equal to 0.05 or 1 over 20 is a much easier way of writing it. We know it starts off going at 20 meters, and we know it's going to travel a distance of 105 meters. And we also know from looking at this side, we have a change in height, which is going to be this side of your triangle, essentially. So let's first get an expression for our change in height, which is going to be 105. If this angle in here is alpha, this side would be 105 cosine alpha, so this side would be 105 sine alpha, which is handy because we've already been given sine alpha. It's kind of a clue you're doing the right thing. So that's going to be 105 over 20. And that means that your change in your gravitational potential energy is going to be calculated like this, which is going to be still 850 because it's still in the same 9.8, and then we're going to multiply it by our delta H, and when we put all those numbers in, you end up with 5. So we've got our change in gravitational potential energy there, this number. Let's leave that there. We now need to work out what the change in, or generate an expression for the change in kinetic energy, which is going to be going like this. And remember, we don't know what our final velocity is, so I'll leave it there as v squared. And we also know the work done against resistive forces is going to be the force times the distance which is going to be this many. So then we need to think about what's going to happen. So you start with kinetic energy and you lose kinetic energy but gain gravitational potential energy and do some work against friction. So that means your change in kinetic energy is going to be equal to the change in the gravitational potential energy plus your work done. And that means that if we multiply some of the numbers in the kinetic energy expression, we end up with this number here. And we know we've already calculated these other values earlier. And if we rearrange and solve this equation, we will find that your V is given by square root 425 times 400 minus 1277.5, and that's all going to be over 45, which gives you 9.97 meters per second as your final speed after all of that work and energy change. Okay, so that is the end of question 1. I will pick up question 2 in the next video.